there is something called as VIF, variance inflation factor. If this value is greater than 10, that means there is collinearity problem. This is a formal way to assess the collinearity. So let me run this VIF. Okay, there is some package which is missing. Yeah, so car is a package. Um, which has to be installed and loaded before you do VIF. So again, I'm telling you, it's very exploratory. Look at this VIF value. Though the thumb rule says if the VIF value is greater than 10, there is a collinearity. All these four inputs have collinearity problem. Everything is greater than 10, right? But though everything is greater than 10, horsepower and SP were turning out to be significant. Volume and weight were not turning out to be significant in your regression output. So probably there is some problem with this or this. Now what to do? Delete either weight or volume, or try to transform the data. When I say transform the data, maybe you have to take log of weight, log of volume, and then try to regress and see whether you're getting the desired output or not. If log is not working, take exponential transformation, do reciprocal transformation, do a square root transformation, do a cube root transformation, or do a box cost transformation, do a Johnson transformation. And let me tell you this, if the client gives you 6 months, you can continue to work for 6 months in building the same model. You can perform umpteen number of operations on this. If the client gives you only 1 week, then you'll not do any transformation, simply delete this or this, and then run the model and give a model to the client. The more the time that you spend, better will be your model. Now, which one to delete? I would get to that in a moment. Obviously, you know for a fact that from this, I feel that VAF value is very high for weight, so we can probably delete this. But let us also double confirm before deleting anything, right? So before deleting any observation or any variable, first we need to check on whether you can delete one of these 81 entries. So notice clearly, if I delete this weight, I would get rid of how many rows? 81 rows, because we have 81 rows. This entire 81 rows for weight is gone. Instead, if I can somehow find out on whether any specific row can be deleted, and because of which can I get rid of this problem, that is another thing that you need to look at. Because if you delete a single row, how many values are you getting rid of? 1, 2, 3, 4, 5. However, if you delete the entire column weight, how many entries you're getting rid of? 81. Deleting each data point has to be done with caution, because collecting the data is such a difficult task and costly affair. I didn't get you, Smitish. Mostly they asked to determine that. Means? Yeah. So normally you do not give a single proposal, right, to the client. You'd obviously say, hey, it depends. If you want an accuracy of greater than 60%, less than 70%, then the timelines would be 1 month. If you want accuracy of greater than 70, less than 75, then 2 months. As and how you keep increasing the accuracy, increase the timelines with to a great extent. 3 months. Greater than 95%, I would say give 1 year. Again, it depends on the industry that you're working with, so on and so forth. That you'll come to know. It depends on different companies. And the moment you guys become data scientists, probably I'll be getting in touch with you all to know how your organizations are working so that I can take some best practices from you all. All right. Now, uh, let me go to linear regression modeling. This is the prediction model equation, right? One more thing that I forgot, friends. Whenever you're predicting a value, it's represented using a hat. Otherwise, it's given. This is predicted value. This is the actual value. Whenever you have predicted values, it's hat. Whenever you have a predicted value of beta naught, it's beta naught hat. Okay. So line is the assumption. Whenever you build a model, it is not something that you have built a model, job done, wash your hands, go home. Even before you run that model, even before you finalize the model, you need to ensure that the model assumptions are satisfied. And line is a model assumption. L stands for linear, I for independent, N for normal, and E for equal variance. Linearity, you know how to find out linearity in the various parameters using scatter diagram. You can do that. Okay, Sushant has done that research. SP in previous example stands for top speed of the car. Thanks for that, Sushant. Okay, so that means these coefficient values should enter linearly into the equation. I can put a square here. It will become quadratic. But what I'm interested in is whether these coefficient values or parameters or estimates, are they entering linearly into the model? Of course, scatter diagram is the best bet for that. Second thing is assumptions about the errors. Errors. Error is what? Predicted value minus actual value. Your error should be independent and identically distributed. If you take average of all your errors, it should be 0. If you calculate the variance, it should be constant. And if the variance is constant, it is called as homoscedasticity. That means there's no problem. However, if there is no constant variance, it is a problem of heteroscedasticity. And one more thing is these errors should be independent of each other. Errors should be independent of each other. If they are not independent, then there's a problem called as autocorrelation problem. Guys, spend a lot of time on this slide and this recording. Go through at least 20 times if you do not understand. This is heart of your uh, entire data analytics. Okay, because majority of the times you will have continuous output and then you use linear regression. And assumptions about the predictors. Predictors are what? Inputs. They should be non-random, meaning you should have determined your historical data upfront. Non-random means historical data is decided upfront. You have the data with you. And measured without error, we are assuming that there is no data entry error, or the measurement system is reliable when you have collected the data of inputs. These inputs should be linearly independent of each other. If they are not independent of each other, there is a collinearity problem. Here we are discussing about independent inputs. Here we are discussing about independent error values. And finally, all of your observations should be equally reliable. So all the entries that you have should be equally reliable. It should not so happen that, hey, I'm giving you 81 rows. Out of these 40 rows, I'm 100% sure it's correct. Another 41 rows, I'm not so confident. Gone. Right? Each and every observation should be equally reliable. Okay. Now, let us try to solve this using the R code. There is something called as plot. Plot does variety of things. Plot in some sense will give you, in some scenarios, plot would give you box plot. Plot would give you, in some scenarios, a box plot. In some scenarios, it would give you a line plot. In some scenarios, or in regression scenarios, you'll get this. Look, let us look into this. This is the first entry. These are the residuals. Residuals or errors mean the same. Errors versus fitted values. As in how your predicted values increase, your errors should not increase or decrease. Your errors should remain constant. Remember, errors should be having constant variance, so on and so forth. Right? So errors should be constant. So it's more or less constant, this red line, right? It's more or less constant. There is no weird representation. If this red line would have been in this way, in this way, this red line, or if it would have been like that, that means we know for a fact that as and how your fitted values or predicted values increase, your errors are increasing. If it was in this way, if it was in this way, as and how your fitted or predicted values increase, your errors are reducing. So this is fine. Now you need to keep pressing enter, enter. This is called as normal QQ plot, quantile plot. This is used to check whether your errors are normally distributed or not. If all these data points fall along this line, majority of the data points are falling along this line, right? Hence you can say that errors are normally distributed. Here we have errors, residuals are errors. But one key thing that you notice here is 77 and 71. Just remember those, don't worry about those now. Okay, did anyone leave? Oh, Vishal has gone offline. Huh. Now let me enter. I'm also standardizing the errors. I think I have to also explain what is standardization. So I'm standardizing errors for now. Just remember that I'm making it unitless. When we standardize, we are making it unitless. I think yesterday I've discussed during PC, I believe. Standardizing means making values unitless because volume has one unit, horsepower has a different unit, top speed of the car has a different unit, right? And then weight has a different unit. Hence, I'm standardizing and then checking. Here also you have a straight line. That means there is no uh, a trend as such in the data. You have there is no trend in the errors basically. And finally, the last plot, which is called as Cook's distance. Remember from the Cook's distance perspective that if this Cook's distance value is greater than 0.5, that means that observation is influential observation. Assignment for you all. What is the difference between influential observation and outlier? What is the difference between influential observation and outlier? So if you see here, there is one value which is falling beyond 1. So anything greater than 0.5 is influential observation. So 77 is influential observation.